The author of the idea of a space elevator is Konstantin Eduardovich Tsiolkovsky. In 1895, while inspecting the brand new Eiffel Tower in Paris, Tsiolkovsky thought about how it would be realistic to build a tower as high as geostationary orbit in order to deliver cargo directly into space through it. The design turned out to be practically unfeasible, moreover, that its foundation on Earth would be comparable in area to all of Paris, so even the strongest steel would not withstand such a load. However, the idea of a tower or mast going directly into orbit can be attributed to the impossibility of the first class. In accordance with the paradigm of Michio Kaku, the creation of such a structure does not contradict the laws of physics. We simply do not have the materials and technologies to implement the project. The next, quite applied attempt to approach the idea of a space elevator was already undertaken in the USSR in 1960. July 31 in the Sunday supplement to Komsomolskaya Pravda. The article Into Space, on an electric locomotive was published, written by Yuri Artsutinov, who at that time was a postgraduate student at the Leningrad Technological Institute. Then, space launches have been going on for the third year, but a man has not yet been in orbit. Yuri Nikolaevich rightly noted that space flight on a rocket could not become a mass phenomenon, as it exerts exorbitant loads on the human body, and also requires an unacceptably large amount of resources and energy to be spent to overcome gravity. Therefore, Artsutinov suggested, rockets should be launched from orbit, where they can easily acquire a second space velocity and go in the right direction. For this purpose, a whole city with greenhouses, observatories, solar power plants, workshops, fuel depots, and landing devices for interplanetary rockets should be deployed in orbit. The delivery of people and goods to such an orbital station should be carried out along a vertical route 50 to 60,000 kilometers long, since for a metal structure of this size at an altitude of approximately 42,000 kilometers, the centrifugal force, due to the orbital rotation of the Earth, will become approximately equal to the force of gravity, under which the structure could crash to the ground. Accordingly, such a structure would have to be composed of a ground-bearing part, which has a variable, increasing thickness on the way to geosynchronous orbit, and a counterweight, which starts at an altitude of about 42,000 kilometers and balances gravitational force by its own centrifugal force. Artsutinov intended to equip the open-work structure of such a mast with railway tracks operating on the principle of a maglev train. The train should gradually accelerate until it reaches the first cosmic velocity. Moreover, it was only the magnetic field that had to drive it up. In this case, the fuel would not spent. Here I will briefly dwell on practical considerations that make it possible to realize the benefits and even the necessity of a space elevator. The space elevator is technically unrealizable at present, primarily because we do not have the technology to commercially produce nanotubes or similar light and strong material from which it would be to assemble such an elevator. However, a space elevator, unlike, for example, a hyperloop, is not an improvement on any existing technology. It is fundamentally new, environmentally friendly, and in the long run, also economical project. Space elevator opens real opportunities for long-term near-Earth colonization. Orbits, colonization of the Moon with the ability to arrange expeditions to any point of our satellite. The space elevator is one of the most realistic prerequisites to master Lagrange points, which, in turn, may be convenient for the industrial processing of asteroids. Finally, the space elevator is an indispensable technology for landing on super-Earths and safe departure from them. Now let's talk about everything in order. Approximately in this form, the space elevator was presented back in the 1960s. Returning to the tower model of the space elevator proposed by Tsiolkovsky, we note that the gravitational force will act in the opposite way on the sections of the tower located below and above geostationary orbit. The lower part of the tower will tend to fall to the ground, and the upper part will fly into space. Therefore, to stabilize the tower, it is enough to position its center masses well above the geostationary orbit. The Earth's gravity acting on the elevator will be the smallest on the surface of the Earth and the largest in geostationary orbit. Above the geostationary orbit, there will be practically no attraction, and it is there that it is appropriate to deploy the first long-distance spaceport. The next fundamental difference between a space elevator and a traditional one is the immobility of the trunk of the entire structure relative to the Earth, of course, relative to the satellites and space stations. The elevator will rotate at the same speed as the Earth. On the contrary, the movable part of the elevator will be the same lift cars that will balance each other, if at each moment of time one of them moves from bottom to top, and the other, from top to bottom. A similar idea was put forward in an article in 2021. Chinese scientists. Way. It can take from a few days to a few hours for such a carriage from the Earth's surface to a geostationary orbit. Since the lifts will perform not only transport, but also a balancing function, they cannot carry fuel with them. Firstly, the volume of fuel relative to the volume of the car would be as large as the volume of fuel required to launch a launch vehicle into orbit. Secondly, as the fuel burns out, the mass of the entire lift, or rather, all the lifts involved, would also change at the same time, which would significantly destabilize and rock the entire system. Therefore, in the Artsutanov model, it was supposed to power the lifts with electricity passed through cables throughout the entire elevator. A version was subsequently expressed that it would be possible to transmit energy to the elevator with the help of lasers. Nowadays, a design in which the elevator uses solar energy looks much more logical, since, for example, along its entire length, it is lined with solar panels. Below I will mention why carbon nanotubes seem to be the only realistic material for building a space elevator. However, already here we can make a reservation that carbon structures, primarily full aerons, can also be used as photovoltaic cells. Thus, it is fundamentally possible to assemble from carbon as a carrier. The design of the elevator, and its power equipment, solar batteries. I will also mention below why this is possible, but not optimal. The base station of the space elevator should be located on the equator, since the launch of the body into geostationary orbit is easier, the closer to the equator the starting point is. At the same time, thanks to the law of Archimedes, the weight of a floating offshore platform will decrease, even if it is as large as an artificial island. At the same time, it is convenient to locate the base station at the equator so that it is far from large currents, while it is in neutral waters, and it is easy to reach it. Container ships of any size were suitable, including those carrying groupage and oversized cargo. So, it is possible to assemble a ground platform for a space elevator already at the current level of technological development. A truly monstrous task is to reach the trunk. Lift up to 50,000 km altitude, so that it does not break long before geostationary orbit, and also find how, and from what, to assemble a counterweight on the other side. Designs. At the same time, the constructed structure must be in the dense Earth's atmosphere and withstand the vagaries of the weather, solar radiation, meteorite impacts, and above atmosphere, and collisions with space debris. Finally, the material necessary for the elevator should in no case be combustible. Putting out a fire at such a height will be almost impossible. It is assumed that only carbon nanotubes have sufficient strength to assemble a space elevator. On the website of Rosnano we read that the coefficient of strength of single-wall carbon nanotubes is 50 gigapascal. This coefficient can be calculated by dividing the rupture force, 70 Nn for a carbon nanotube with a diameter of 1.5 nanometers, by the area of the transverse sections. Such a calculation shows that the strength of nanotubes, according to pessimistic estimates, is 40 gPa, but can reach up to 100 gPa, that is, the cable will withstand the load. 10 tons per section with an area of 1 square millimeter. For comparison, for steel, this figure reaches 4/10 of gigapascal, for a single crystal of iron, 1/3 gigapascal, for graphene, 350 gigapascal. The values achieved in practice for carbon nanotubes and graphene by 2019 are 28 and 94 GPa, respectively. Despite such optimistic indicators, the industrial application of nanotubes is still very far away, since by now it has been possible to grow a nanotube with a length no more than a few meters. As an alternative to carbon nanotubes, even stronger ultra-thin diamond fibers can be used, obtained in 2017 by John Budding's group in University of Pennsylvania. Such a carbon structure was obtained by compressing benzene molecules under a pressure of 200,000 atmospheres. As a result, carbon atoms are reassembled into an extremely strong crystal lattice, the cell of which resembles a tetrahedron in shape. From a physical point of view, the length of carbon tubes can be practically unlimited, but even a material as strong as graphene will certainly not withstand growing up to geostationary orbit and collapse under its own weight. A revolutionary solution that allows solving this problem already at the current level of technological development was proposed by Zephyr Penwar and Emily Sandford in 2019 year. Perhaps it would be more realistic not to build the first stage of the space elevator from the Earth, but to hang it from the Moon. Lagrange points and space elevator. In the region of the Earth's orbit, there are amazing places where gravity practically does not act, because in them the gravity of the Earth and another celestial body extinguishes each other. In 1772, these points were discovered by the French mathematician Lagrange, who was interested in whether there was a place in the solar system where the gravity of the Sun and the Earth were equal. It revealed that there are as many as 5 such points where the gravity of the Earth and the Sun and the Earth and the Moon extinguish each other. They were called L1, L2, L3, L4, and L5. If we place a spacecraft at the Lagrange point, or, for example, a space station, he, A, will not go anywhere from there. There are definitely Lagrange points in other objects in the solar system, for example, apparently, it is in. At such a point between Mars and Jupiter, the asteroid Achilles sat down. The idea of Penwar and Sandford is as follows. If you could build a space elevator base on the Moon, attach a thin carbon fiber cable there, and then stretch it through the Lagrange point in the direction of the Earth, then at this point it would be possible to begin the arrangement of a permanent colony halfway between the Earth and the Moon. Since there would be no natural gravity at such a station, it would be relatively easy to get to any point on the Moon from there. Would become technically. Regular lunar expeditions are expedient, including for the most valuable helium-3 necessary for the development of thermonuclear energy. From this station, in turn, it would be convenient to pull the space elevator towards the Earth, collecting at the right point the counterweight that will provide the necessary tension for the Earth, Lagrange point section of the elevator. More information about the potential use of Lagrange points in astronautics and, in particular, in the exploration of the Moon is described in an article from the website gagarin.ru, where questions from a journalist answers Doctor of Technical Sciences Yuri Petrovich Ulybyshev, Deputy Head of Energia Corporation. In this case, I want to emphasize 2 more important aspects related to the descent of the space elevator from the Lagrange point. Firstly, such a configuration greatly facilitates the construction of an orbital stabilizer counterweight, since the materials for it will be literally at hand. Space debris and used artificial satellites can be used to assemble the stabilizer. Secondly, the stabilizer could be reinforced with metals from a small an asteroid, which could also be moored to the station only in conditions of negligible gravity. Moreover, in the future, the technology of a descent space elevator, from natural satellites or from Lagrange points, could become indispensable for the development of super-Earths. As is already known today from the results of the work of the Kepler telescope, stone planets are widespread in our galaxy, similar to the Earth in chemical and, possibly, geological composition, but exceeding it in size by 2 to 3 times. There is an assumption that such planets may be superinhabitable, as they can hold. There is more water on the surface and denser saturated atmospheres. But at the same time, they are real gravity wells as for any manned expedition from Earth. And for potential aboriginal astronautics. The first cosmic velocity on the super-Earth is so great that to enter its orbit using the usual, we would need a booster rocket the size of the Pyramid of Cheops for fuel. Therefore, perhaps, the inhabitants of such planets are simply locked in their worlds. Accordingly, as with inhabited, and from an uninhabited super-Earth, even an earthly ship that happened to be there could not fly away. There wouldn't be enough fuel. But the development of super-Earths is greatly simplified with well-established space elevator technology. Even if the super-Earth does not have a convenient satellite, there will certainly be. It will be possible to find a convenient Lagrange point and unwind a carbon fiber, or similar, more durable, cable to a mountain peak on this planet, by the way, due to the reinforced. The gravity of a mountain on a super-Earth should be comparatively low. But here I am getting too deep into science fiction. An important critical vulnerability of a carbon space elevator that should be considered here is the flammability of carbon fiber. Carbon nanotubes don't just burn, but they flare up. Therefore, it is assumed that silicon, rather than carbon, can become a safer and at the same time strong material for the production of such tubes. Silicene is a silicon analog of graphene. Silicon crystal lattices are much more difficult to obtain than graphene. However, silicene was observed in 2010. And in 2012, to grow artificially. Initially, certain hopes were associated with silicene in the semiconductor industry, but practice has shown that it inapplicable in microelectronics, as it decomposes too quickly into ordinary silicon. I could not find materials on the practical production of silicon nanotubes. Analog carbon O, based on silicon. On the other hand, it is precisely when reinforcing a space elevator that silicene could come in handy, also because which should be easily integrated with microelectronics, also created on a silicon basis. Perhaps it will be possible to organize inline production of silicene fiber using 3D printing. Conclusion. I am aware that at the time of writing this publication, the creation of a space elevator is far beyond the capabilities of mankind. Even Elon Musk, known for his large-scale projects, declined to comment on the topic of the space elevator. I deliberately bypassed here the purely economic benefit of such a project, potentially. The space elevator would make it possible to reduce the cost of delivering 1 kilogram of cargo into orbit from $20,000, now, to $500, with the prospects described here, the elevator could to work downhill no less actively than uphill. I hope I have managed to fend off all or at least some of the criticisms from the article. Will we have to say goodbye to the dream of space elevators? Released in 2015, and give you food for thought. Thank you for your attention. Subscribe to the channel. I assure you, there are many more interesting things ahead of you.